In today's video, we will look at the problem cryptcowgraphy. So here we have this long string, and we want to basically see the sections where it's cut off by the C, O, and W. And we have to swap whatever is in between there. For example, here we have a capital C here, capital O here, and capital W here. So we should swap these two. So we should swap whatever is in between the C and O, and whatever is in between the O and K, or the O and W. And so here, first of all, what we can do is write the basic code for this. We'll have to improve this a bit more later on, but here this is the basic code. So we basically use recursion to loop through every of the possible ways that you can arrange these C, O, and W's. So first, I will create this first loop to look at to find all of the C's, and then I will use the second loop and start at this position +1 because they have to be the C, O, and W have to be in consecutive orders. So here, now we see if there's another one that's equal to O, and then we find another one that is that's at an index even bigger than this O, and then also check if that is equal to W. So if these match, then we should swap whatever is in between these CO and OW. So to do that, we will use the substring function. And first, the beginning, so whatever is before the C will remain the same, and whatever is after the W will remain the same. So this is after the W, and this is before the C. So here we have all the indices stored in here. This is the first part. The first part, this is the part from O to W. So we should put this in front of this C to O because we're swapping these two places. So here this thing will be the words that are in between O and W exclusive. So we shouldn't include the O and W since we basically used them already. We swapped it, and now we don't have to look at these two O and W's and C's anymore. So we can exclude the C, O, and W and look at the rest of the string after we swap these two middle parts. And then after we swap these middle parts, we will use this search function again and put this string into our search function again, just like this one, and then we use the search again to basically keep on going until we finish using all the CO and W's. And then once we finish using all of the CO and W's, we check if this string is equal to what it's supposed to say. So it has a specific sentence that's supposed to say here. So begins a execution at the break of dawn. So it's supposed to spell exactly that with the capital and specific spaces. So if it's equal to that, we should return true and print out how much moves do we use to decrypt this whole thing. And otherwise, if it's not equal to that, this means this current way is not possible. So we will return 0, 0, meaning that this is not there's no way for this current combination. And here, if you submit this plain solution, you will get time limit exceeded at case 6, and there are 10 cases in total. So we can think of a few ways that we can do to optimize this. So the first way here is that we can recognize that no matter what we do, just count. So this total number of moves used to decrypt this whole message will be the total number of cows in here. So the total number of COWs in here. And to do that, we can basically subtract away the length of this original string, and then divide that by 3. Divide the remainings of the subtraction by 3, and that will give us the total number of CO and W's that we have. Basically, meaning that will be the total number of decryptions that we will use, because this will definitely be no greater than that, since here we have only that much amount of CO and W's. We cannot do any more swaps than those. So this is the first way for us to optimize this. We can basically check if our C is equal to the string that we're looking for. So outside here, we can create a string that we're supposed to be looking for, and that is basically this whole string. So we can set this to equal to the original string, and this original string should be like this. And now we check. Now we also create another variable to keep track of the total number of moves that we should use, because this is already calculated in before this. So we can set v to equal to the size of our current string minus the size of the original string that we're looking for, and divide all of that by 3. So this way you will be able to get the total number of C, O, and W's inside this current string, and that will be the total number of moves that we need. So here we can stop right away when we find some moves that's already equal to this current value V. And since we started 0 moves, we check all the way. So if it's equal, we will return if this current S is equal to the current if this current S is equal to the original string. If it is equal to that, then we don't have to loop anymore. We can stop this right away. And so here, this way and then here for this we would just return this CNT, or we can return V. Basically, it's the same thing, since at the end CNT should be equal to V. And here there's a special case. That's if this is 0, it means that this returns false. Then we should also print out false for this one as well. So here inside our main function, we'll just check if it's false for the first part of this answer. Then if it's false, it will mean that it's not possible. Then the second part of the answer should also print out 0. So then here when we print out the two values, we'll get 0. And then there are a few other cases. For example, let's see, everything that's before the first C should remain as the same as the original one, because if it's before the first C, there's no way we can swap anything in here. So this first part should be exactly the same as the first part in the original string, and this is the same as the last part. So anything that's after the last W should be equal to the same thing as the original string as well. So the suffix and the prefix must be the same. And then for these middle parts, we can look at all of the parts, all of the sections between the C, O, and W's. So for example, here we have two parts. This part is between this C and this O, and then this part is between this O and this W. So now we check if these two parts actually exist inside our original string. So we check if we can use string.find to find if this position in the original string where this will fit. And it's also the same for this one. We also check if there's a position where this string fits inside the original string. If it's not, if the final substring is not found, then we should return false right away, because that means there's no possible ways for us to get to the original string, since these sections here are since the sections in there don't exist inside the original string. There's no way we can get those in to become the original string. So here, this is the actual code that can pass all of the test cases. I will create this check function to check all of these cases. So this is the first part, and this first part is basically checking the prefix, and then this second part is checking the middle part, and then this final part will check. So this final part will check the suffix, and then and this is the part that checks the middle, and this is the part that checks the suffix. And we can stop the we can return false anytime we meet one of the conditions that are not correct. So here we first start at the beginning of this, and then loop all the way to either the end of this current string or the end of this whole original string. So we use minimum size for these two, and then we so we will keep on going until we reach the C. So if we reach the C, like I said, since anything after the C can be rearranged because there will be O and W, so you can swap those positions, but anything before this first C must be the same as the original string. So if it's already a C, then we can stop this loop. The prefix is already done. And otherwise, if it's not equal to the original character, so if this character at this index I is not equal to the original character at index I, we should return false, basically meaning that this current string is not possible to form the original string. And this is the same for the suffix. But for the suffix, you have to start at different positions. For our string position, we should start at the end of the current string. And for the original string, we should start at the end of the original string. Another way to do this is by also getting a reverse of this original string and also getting the reverse of this current string and checking that the same way as checking the prefix. But here we can start at the end and then loop all the way to the beginning. So we also stop when we reach the W because we're going in this direction, starting at the most end, and we will stop when we reach this capital W because anything before the capital W will be able to be swapped around. So here we only check whatever is after the first W, the last W. So if it's not equal, we will return false. Otherwise, we will keep on going in the loop and also decrease our position index by 1 every time. And then checking middle is also the same, but here we only check the sections between the C and O's and also W's. So here this T will keep track of where our first index is. So basically just keep track of our last index where we encountered a C, O, or W. And every time we encounter a new C, O, or W, we will check the string between that section. So we get a substring starting at our T. So T is the last one that's not C is the last character that was not C, O, or W. And to get the length of the substring, we will do I minus T. This will give us the length that we should get. And we use the string.find. So we try to see if there exists this string inside our original string. If it doesn't exist, then it will be equal to the string's n position, basically meaning that it doesn't it's a null position, so it doesn't exist inside this main original string. So if that's the case, then we should return 0. Otherwise, we can set our t to I plus 1 because here at the index I will have one of these values, so one of these characters. So we should look at the plus 1 for this since we're looking at the strings that are not containing any of these C, O, and W. And so any of these false cases will return 0. And finally, if it passes all of the checks, will return true, meaning that the string might be possible to be arranged into the correct position. So this part saves a lot of time. And then there's another part where we can use an unordered map and string hashing to keep track of the ones that we already visited. So we don't have to revisit the strings that we already visited, just like in graph. In graphs, we don't have to revisit the nodes, and here we don't have to revisit the same strings. So we will use this hash function using the C++ hasher, and here you can give it anything. It can also be int or anything else, but then that will just remain as the value itself. So here you can hash the string into a super long integer or super long number, and then we will use that to store in our visited unordered map. Here we shouldn't use a string directly because that's going to waste a lot more memories than changing it into a hash and then storing the long value instead. So here, this is still our the basic code is still the same. Still loops through all of the C, O, and W, and also get this substring like what we just did in the original code. And then we check if this current string is possible to form the original string. If it is possible, we will get the hash of this current string and check if we've already visited that hash. If that hash is already visited, it will mean that the string is already visited. So we can continue on to the next string because we don't have to look at this again since we've already checked it before. And otherwise, we will set this hash to visited, so the next time we won't have to loop through this string again. And we get the result for the search. Also here, we also put in this to make sure that our total number of moves is always equal to the maximum number of moves, or the number of moves that is definitely required for us to decode this string into the original string. Then we'll just return if they're equal. So here, we don't have to use a pair anymore in this function, because now we definitely know what the total number of moves will be. So we just have to return if it's possible to form that number of moves or is it not possible. And every time we will still use this recursion, but here every time we do the recursion, we will use this check and also hash this and check if it's visited. And now we get this and store into a result. And if this variable is already set to true, just means we've already found a way for this current string to become the original string. Then we should just return this result, or we can just return true, because we only return true if this result is true. And otherwise, if we've gone through everything and still didn't find any of these possible moves, then we'll return false. Also here in the main code, I will also add a few things. So all the way up here, I created two unordered maps to keep track of the total frequency of the characters inside both strings, the original and the current strings that we just read in. So first, I will store all of the frequencies for the characters in both strings. This will keep track of the original string. So for each of the characters in there, we'll increase that character count by 1. And this is the same for the current string that we just read in. We also increase the character count for that by 1, but in a different unordered map. Then we'll loop through each of the characters inside our original string. And if the number of characters inside the original string is different from the number of characters for that character inside our current string, then we should set this f to false and stop this loop. So later on, we'll just set the answer to 0, 0, because we know that's definitely not possible since the number of characters are different. And there's also other cases, such as when the number of C, O, and W's aren't matching. If they don't match, then there's definitely going to be some leftover C, O, or W's inside the final string that we get. So that will also turn f into false, because there will be no possible ways for us to get the actual string if we have any of these leftovers characters. And then here we still do the same thing. Get the size of this current string minus the size of the original string and divide that by 3. This gives us the total number of moves that we're definitely going to make. And then here we see, we check these few cases. If our f is equal to 0, this means that the frequencies don't match up. Then it means that there's definitely no possible way. Then our answer will be just set to 0, 0. Otherwise, we can try to search through all of the possible combinations with a few pruning by checking and making sure it's not visited over and over again. And then the total number of moves should be what we just calculated here. However, here, if we just do this, we will the search might return false, but our total number will still be something. But here in the question, it stated that if it's false, then it should just return 0 as well for the second value. So I check if this first value is equal to false. So if this search returns false, it means that there are no ways for us to get this original string. Then our second value should also be set to 0, meaning that basically just returning the case like this. And then finally, all we have to do is print out the first part of the answer and then the second part of the answer.